How and to what extent are the James Webb Space Telescope images recognizable? Much of the credit for the breathtaking appearance of the Carina Nebula in the first photographs from the James Webb Space Telescope goes to Alyssa Pagan. She's an expert in the Space Telescope Science Institute, where she helps turn Webb's raw data into stunning photos. Pagan says that the work was done by partnering artistic ideas that came from science, facts that are true, and personal choice. The vast distances between Webb and the things seen make collaboration essential. The infrared spectrum significantly expands JWST's observing capabilities. Pagan and his group must determine the most effective means of disseminating infrared data to the general public. If the filmmaker makes these choices, the audience may be able to find more meaning in the film than meets the eye. For instance, Pagan is often sought for commentary on color schemes. During several exposures, JWST records data in narrowband or very narrow ranges of wavelengths in the infrared spectrum, which correspond to the number of certain elements like hydrogen, sulfur, and oxygen. Following that, we use chromatic order to assign a different color to each of them. Short wavelength colors, such as blue, are linked to oxygen-like ions. All of them will be stacked atop one another to form the finished sculpture. Even though hydrogen and sulfur bands are often linked to red tones, they are often filtered via a yellower filter to offer better clarity. This led to the widespread adoption of a color scheme called the Hubble palette, so named because it was initially extensively used in combination with the older telescope. Fake color and colorization are common ways these pictures are described. However, Pagan is certain that the colors are accurate representations of reality. They might serve as a map or compass for the savvy viewer. In Webb's picture of the Carina Nebula, the lower red part is mostly made up of hydrogen and sulfur, while the upper blue part is mostly made up of oxygen. A lot of individuals use this technique when they need something to seem mysterious or even alien. Pagan says you should choose a base color palette before letting your tastes take over. She could manipulate the color spectrum in any way she pleased, from blue to purple and back again. The bright colors against the dark background are reminiscent of the Carina Nebula. Objective changes are also made, like reducing artifacts like scattered light from the telescope. At this point though, the results from two computers may be very different. According to Pagan, I adore making things look more ethereal and lovely. Since this is outer space, my approach has a lot of freedom. Making people feel something by showing them pictures of space is nothing new. Scientists who focus on the analysis of moving images, Dr. Elizabeth Kessler, is almost done writing a book about how comparing familiar images to those in this exhibit makes us more amazed by the universe. Visual artists on the Hubble team made comparisons between the universe and familiar places on Earth so that people could better understand the project's scope. To put it another way, JWST will use the same strategy. Kessler's book cover depicts an image of the Carina Nebula that the Hubble Space Telescope took. When first used, this phrase meant hills and valleys. Another name for the structure shown in NASA's most recent photograph is cosmic cliffs. Nothing about this unconventional depiction of the Carina Nebula was done by chance. In an interview with The Verge, Kessler talks about how important cropping and orientation decisions are. There are many great places in the nebula to show how stars form, and they painfully chose this area and put it together in this way, she says. An orbiting observatory wouldn't give a hoot if photographs were taken with the north at the top, as is common on Earth, since there's no up or down in space. This picture flip caused the dust cloud to seem extremely powerful on your screen, as Kessler put it. Pagan wants the pictures to be mysterious, but she also wants the ordinary person to enjoy looking at them. When processing images, Kessler claims extremely beneficial parallelism is used. The sheer magnitude of what we're seeing now is mind-boggling. We haven't seen anything larger than these mountains. Astronomers study the universe in many different ways. The Hubble Webb method is just one of them. Dylan O'Donnell, a public science communicator, thinks this technique is popular with photographers on the ground partly because it can reduce the effects of light pollution. According to O'Donnell, this technique makes it possible for anyone in the center of a major metropolis to capture shots that look like Hubble images. A central processing unit, or CPU, may choose from a wide variety of color palettes in order to understand such narrowband filters, and this allows it to make decisions about what to record and from what angles to gather data. Another common method is the CFHT palette, so called because it was developed in honor of the Canada-France-Hawaii telescope. A big reason why the Hubble palette and the CFHT palette are different is that the CFHT has a more complex way of organizing colors. Hubble filters hydrogen to make nebulae look yellower by zeroing in on a different potential wavelength. but CFHT moves sulfur up the color spectrum, making nebulae appear greenish-purple and providing additional information. Astronomer Heather Flueling from CFHT chimes in, "It doesn't alter the research. A few traits are accentuated, but that's all." A wide variety of wavelengths and filters may be used to provide various visual effects and data visualizations. O'Donnell made a preview tool that makes it faster for experts to try new ways of doing things and easier for beginners to compare and contrast the different options. Choosing a filter is an individual process. Even though O'Donnell says most viewers strive for realism, he defends his use of false color to highlight details as an asset to his work. Although the Hubble palette is very practical, O'Donnell warns that it runs the danger of becoming a little cliched due to its overuse. To do this, his method combines the narrow bands of hydrogen and oxygen with the wavelength of green light. Furthermore, JWST produces graphics with unconventional color schemes. Jupiter has recently been the subject of several new images, the most notable of which portray the planet with a blue hue. In contrast to Hubble's previous red and blue images of Jupiter, this new one makes even the infamous red spots seem white due to reflected sunlight. Pagan didn't edit this picture, but he thinks that the redder tones were done to draw attention to the aurora. According to Kessler, the Webb images will have a slightly different path from Hubble's. Webb's future path will be decided by an iterative process that uses data and human judgment. This will connect thousands of years of visual culture with the billions of years it takes for light to travel across the universe. Besides visible light, additional electromagnetic radiation includes gamma rays, X-rays, ultraviolet, infrared, terahertz, microwaves, and radio waves. Rarely do astronomers explore the universe beyond the range of what can be seen. As one concrete example, thermal cameras can detect radiation at far longer wavelengths than the human eye can. Information gleaned through them is complementary to that obtained via the human eye. As an alternative to typical graphs, thermal data could be displayed as color-coded visuals. Regardless of their temperature, all objects emit some invisible energy known as black body radiation. Objects hotter than 6,000 Kelvin, the temperature of our sun, generate mostly visible light, while very hot objects like stars produce most of their energy in the ultraviolet portion of the spectrum. Colder ones, like humans, shift their maximum to the infrared. Space data is now collected over the whole electromagnetic spectrum. Radio waves are useful for astronomical studies because their long wavelengths mean they are less attenuated by interstellar gas or dust. This range of light has the potential to show voids of the universe that are otherwise undetectable. Radio waves can also pass through Earth's atmosphere with little disruption. Astronomers used radio waves to probe the universe since the 1930s, when they first detected a strong signal coming from space that was eventually identified as coming from the center of our Milky Way galaxy. In the 1950s and the 1960s, radio astronomy made a lot of progress that made it possible to study the electromagnetic spectrum. This made it possible to study the universe and collect a wide range of alien waves. The mirrors and lenses used in optical telescopes may also be used to gather infrared information. Infrared and sub-millimeter wavelengths may be the best ones to study the early universe when the first stars and galaxies were formed from clouds of gas. UV radiation is given off by hot things, like young, massive stars or stars getting close to the end of their lives. X-ray astronomy has uncovered hot diluted gases in intergalactic space among galaxy clusters. The objects that create X-rays have temperatures ranging from 1 million to hundreds of millions of Kelvin. X-rays have around 100,000 times the energy of all other solar radiation. Gamma rays have the highest energy of any wavelength in the electromagnetic spectrum. Gamma rays with lower energies may come from solar flares, but gamma rays with higher energies are known to come from supernovae, pulsars, and blazars outside the sun. There's no such thing as a passport picture of an object recorded by astronomy equipment. Oftentimes, these composites cannot be seen with the human eye or even with optical equipment, since they are the result of complex processes involving the combination of several datasets. Black holes and other regions of space that seem pitch dark to us radiate vividly in other colors of the spectrum. Can you tell the difference between these photos now?